Anybody have any questions about the homework? Any problems you'd like me to go over? Okay. Well, uh, we've been talking about the stress tensor. Um, and remember, the stress tensor is a measure of internal loads at a single point in a material. Um, and remember that there's always an equivalency between a stress tensor and a stress cube. So when you see a stress tensor, you should always visualize that stress cube. There's always an equivalence between the stress tensor in parentheses, I'll say, and the Voigt stress. And the stress cube. So like, for example, if you have a stress tensor 2, 0, negative 3, 5, 3, 4, negative 3, 4, 0. Let's say this is in megapascals. I made one mistake here. Remember, this matrix has to be symmetric. So the 1, 2 element has to be equal to the 2, 1 element, and I didn't do that. So let me change one of these so that it makes sense. And that's equivalent to, so here's the cube, showing just the positive coordinate axis faces. So we have 2 megapascals this way, 5 this way, and 3 in the negative z direction this way. The symmetry of this stress tensor means that there has to be a matching 5 megapascal value there, a matching 3 megapascal value here. Then we have 3 going this way, 4 going this way. The symmetry says we also have to have a 4 going this way. And then 0 in the z direction on the z face. Because of the symmetry of the stress tensor, we also can fill in things if they're not, if that symmetry isn't like if the stress cube or the stress tensor doesn't have the appropriate symmetry. So let's say that we start with something like, so let's say we have 4 megapascals, and then we have 2 megapascals going this way, 3 megapascals going this way. And we want to fill in the values so that this is a possible stress tensor. Well, the 3 megapascal stress value on the y face going in the negative z direction has to be matched by another one like this. Remember, they can never chase each other. They have to be going towards head to head or tail to tail. So that 3 matches this one. There also has to be a 2 matching the one that's there. And now all of those shear stresses have a corresponding one to make that, if we fill out that stress tensor now, it would be 4, -2, 0, -2, 0, -3, 0, -3, 0. Okay.
Right, so is that like the X, Y, and Z face? Like the top row with all the X's on the X?
Yes,
face?
that's right.
Which one's the Y?
Yep, each row is a face. That's right. Well, I guess you could also think each column is a face since it's symmetric.
Yeah.
Okay, so now the next thing we need to talk about is the relationship between the stress tensor and the traction vector on each face.
It should always be symmetric, right?
It has to be, yep.
So if you don't get symmetric, you probably
Something's wrong, yeah, exactly. So relationship between the stress tensor and the traction vector on a face. So every face on the stress cube has a vector of force per area components acting on it. Force per area, if this is in SI units, that means that it's in pascals or megapascals or gigapascals or whatever. That vector on each face is called the traction vector. On each face is called the traction, and we'll denote it with a lowercase t, and it's a vector. And each component of this vector has units of pascals or units of pressure. And the relationship between the stress tensor and the traction on a face is this. If you take the stress tensor and multiply it by a unit vector n, and this n is the outward facing normal, and it's a unit vector, to the face that you want to find out about. That gives you the traction vector on that face. Okay, so let's see how that works. So let's say we have a stress tensor that's equal to 4, 0, 1, 0, negative 5, 2, and then you have to have the symmetry. So 1, 2, 7. Say this is megapascals. And we want to calculate the traction for, we'll first do it for the x face, the positive x face. Then we'll do it for the negative x face. And then I guess I'll just do it for the negative z face. That should give us enough to have kind of a sense of what's going on. Okay, so if we draw the stress, I guess before I start answering these, let's draw the stress cube that matches this so we can visualize stuff. So we have 4 megapascals going this way. And we have 1 in the positive z direction. That means that there's also 1 going this way. Then on the y face, we have 5 going into the face and 2 in the positive z direction. And for symmetry, we need that to be matched by 2 going this way. And then we have 7 going this way. Okay, so now let's use the stress tensor to calculate the tractions on those faces. So for the positive x face, we're going to take this tensor, so 4, 0, 1, 0, negative 5, 2, 1, 2, 7. And we're going to multiply it by a unit vector that points perpendicularly out of the face that we want. The face we want is the positive x face. So what's the unit vector that points straight out of the positive x face? Yeah, 1, 0, 0, exactly. So we'll multiply it by 1, 0, 0. And what we get out of this is 4, 0, 1. Now look at the traction values on the positive x face and make sure this makes sense. The x component is 4. The y component is 0. The z component is positive 1. So that works. What? Oh, okay. So the outward facing normal, think of it as it's like the alien in Alien, you know, it's like the vector that goes just straight out of that face. So the vector that goes straight out of the positive x face is like this. And so the unit vector in that direction is 1 for x, 0 for y, 0 for z. Okay, because remember, when I draw these, our coordinate system is always this. Okay. So now we're going to do it for the negative x direction and calculate the traction on the negative x face. So we have 4, 0, 1, 0, negative 5, 2, 1, 2, 7. And what's the outward facing normal for the negative x face? Negative 1 for x, and then 0, 0. Do this calculation and you get negative 4, 0, negative 1. Well, on the stress cube, we never draw the negative x face. Do we have any way to know what the traction values are on there? remember that when we were kind of going through that rough derivation of what all the stress tensor values were, we said that in order to be in static equilibrium, in force equilibrium, we needed on opposite faces, we always had to have those elements be equal and opposite. So since that negative x face is equal and opposite to this, those components just need to be opposite signs. And so, yeah, that's the traction on that negative x face. Okay. So now we'll do one more, the negative z face. So we have 4, 0, 1, 0, negative 5, 2, 1, 2, 7. The outward facing normal is 0, 0, negative 1. So we get 1, 2, no, negative 1, negative 2, negative 7. These are all in megapascals, by the way. So is there any way to look at the stress cube and tell if this makes sense? Well, yeah, we can look at the positive z face, and then it should be opposite of all those. So on the positive z face, we have a positive 1 for x, a positive 2 for y, and a positive 7 for z. So we expect on the negative z face to have negative 1, negative 2, negative 7, and that's what we got. Okay? Yeah. Tell me when to stop. Okay, sure. Okay, so that gives us the tractions on the faces of that cube, but it's not real clear yet what the benefit is of this multiplication thing, since you can just look at the cube. But notice that the orientation of the stress cube is arbitrary. You know, our stress cube is aligned with our coordinate system. But if you think about the definition of the stress tensor, there's no reason that that cube needs to be aligned with the coordinate system. So ours is aligned with the coordinate system, but it doesn't have to be. So we can use this traction idea this traction calculation to find the tractions on faces at other angles. You know, at angles that are not perpendicular and parallel to our coordinate system. And this is actually going to be a really useful thing for us. And it connects to calculating stress tensors in different coordinate systems. And we'll see that it connects to calculating principal stresses, which is going to be a big deal for us. So for example, let's say that we have a stress tensor in our coordinate system that's equal to 1, 5, 2, 5, -4, 0, 2, 0, 8. And we want to know what would be the traction on a face that's rotated like this. So here's, let's say this is our XY coordinate system, our XY axes, the Z axis is coming straight out. And let's say the face that we want to consider is at an angle like this with material over on this side because we need to know which direction is outward facing from the material, where this angle is 60 degrees. Okay, so we're talking about the same uh, material point. We haven't changed anything about the loading or anything. We're just calculating the loading that would be on a face if we had arbitrarily chosen our faces to be at a different orientation. Okay, and so we're going to go. So 152, 5, -4, 0, 2, 0, 8. And then we need an outward facing normal for this face. Well, an outward facing normal would be like this, where this angle is 30 degrees. So this is going to be the cosine of -30 degrees, the sine of -30 degrees, 0. And so we have 1, 5, 2, 5, -4, 0, 2, 0, 8. And we're multiplying that by 0.866, -0.50. And let me calculate. This traction idea is the basis for first expressing the same stress tensor in a new coordinate system. And to understand what that means, think about vectors, because tensors and vectors are very similar things. You know how if you have a vector in one coordinate system, it has a certain set of components. And then if you want to express it in a new coordinate system, it has a different set of components, but it didn't change what the vector was. The vector still has the same orientation in space. It's kind of the same thing with a stress tensor. If you express a stress tensor in a different coordinate system, the numbers are different, but it's still the same thing. Okay, so you can think of this as similar to expressing a vector in a new coordinate system. And then the second thing that this is the basis for is principal stresses. We haven't talked about what principal stresses are yet, but they're very important for predicting failure in materials. Okay, so that's all we need to say about stress tensors right now. Now we're going to go on to strain. So remember that stress is a measure of internal loading at a point. Strain is a measure of internal deformation at a point. So, okay, let me get that in here. Stress is a measure of internal loads at a point. Strain is a measure of internal, don't say internal, let's say is a measure of local deformation at a point. And remember, as we're doing this, that what we're trying to, what our work, we're working our way towards is a relationship between this stress, which is loading, and strain, which is deformation. Um, and something that you've seen similarly before is a spring that relates the amount of deformation in the spring, how far you stretch it or compress it, to the amount of force that's applied to it. Okay. And that's the law that you use there is Hooke's law. So we're basically working our way towards a Hooke's law, but for this more complicated set uh, of loads and deformations. Okay. So that's what we're heading towards. Um, uh, for the most important engineering materials, there is a range of loads where the relationship between stresses and strains is linear. Um, and so we're going to call these materials Hookean materials, like Hooke's law. And actually, you might have wondered this before when you were in physics 1, especially when it was like 2:30 in the morning and you're trying to understand something about springs. Like what's the point of all this study of springs, Like what do we care about springs? Like why are we spending 2 weeks of this class talking about things that we keep in our junk drawer or whatever? Like springs don't affect my life. Why do we keep, you know what I mean? Why do we keep talking about them? Well, really, the reason that understanding springs is important is because a lot of materials that we do interact with in our daily life behave like springs. And so, getting that first glimpse at the behavior of springs is getting you ready for stuff like talking about the deformation of steel beams and things. Okay. Relationship. Yeah. Um, one thing I want you to notice, keep in mind, for engineering materials, steel, concrete, even wood, bone. Um, for engineering materials in the linear range or the linear region, so before the forces get so big that permanent deformations happen, strain values are going to be really small. Um, that is less than about 10 to the minus 4. Okay, so anytime in this class that you see strain values bigger than about 10 to the minus 4, you should think that could be a concern about how realistic these calculations are. Okay. Um, this is what a deformation, a local deformation at a point looks like. So if you start with, like you can think of starting with a stress cube, you can think of this as infinitesimal or else just very, very small. So this is an infinitesimal, undeformed point in a material. And it undergoes a deformation. And in general, this cube is going to take the new shape of a parallelepiped, which means every face is a parallelogram. Um, so this is the deformed cube. Um, I've drawn it so that you can see what the new shape is, but it's going to be, I mean, that's a way, way exaggerated deformation. Steel doesn't do this, concrete doesn't do this. So you really would have smaller changes. Um, so in this deformation from a cube to a parallelepiped, two things happen in the deformation. And we're going to think of them as two different things. The computer needs a break. So two things happen during this deformation. The first one is their length changes. And if you look at this picture, you can see, like, for example, from the top to the bottom of the face that's pointing at us becomes longer, and from left to right becomes shorter. Those are length changes. And these are represented by the normal strains. And then the other thing that happens is angles between edges change. So the second one is angle changes. And those are represented by shear strains. And when we talked about the stress tensor, we talked about normal stresses and shear stresses. We have a similar thing here, normal strains and shear strains. And I'm going to talk one by one about what each of these two things looks like. So we're going to start with normal strains. So if you start with, let's say it's a cube, we're looking at it straight on, so it just looks like a square to us. We start with length sizes L sub 0, and then the deformation happens, and we're going to ignore the angle changes for now. But you end up with a new length along the x-axis, Lx, and a new length along the y-axis, Ly. Yes?
Can one of the lengths remain the same?
Yeah, they can stay the same.
Like Lx is different from the original horizontal line, but the vertical line distance length.
Yep, they can totally do that. Yep.
It doesn't have to be like the same total length. It can just,
Right. Yep. And the names of these normal strains, the one in the x direction, we're going to call epsilon xx. I'll just call it exx because it's easier to say, but it's the Greek letter epsilon. And this is defined as the deformed length along the x-axis minus the starting length divided by the starting length. So if these lengths, we're taking these lengths in meters, what are the units of the numerator of this fraction? Meters. What are the units of the denominator?
Meters.
And so they cancel, and so these are unitless. It's just a number. Now EYY, you can think of that as the Y normal strain, is defined as Ly minus L0 over L0. This is also unitless. And the one I didn't draw because it's out of the page and into the page is the Z normal strain, and that would be your deformed Z length minus L sub 0 divided by L sub 0, and that's also unitless. Yeah. Well, I did it starting as a cube, and so they're all the same. But if it was starting as like a rectangular solid, then you would use the starting length along that axis. One thing to notice about these is what the signs mean. So a positive normal strain, look at that definition and tell me, does that mean that the length is increasing or decreasing? Yep. So a positive normal strain means it stretches, and a negative normal strain means, I'll just call it contraction. And all of these signs are starting to match. If you remember, a positive normal stress means that the material is being stretched, and so you would expect that stretching, the tension on the stress cube to correspond to the material increasing in length. Okay, let's do an example. So let's say this is our undeformed chunk of material. Let's say this is 1 centimeter, so 0.01 meters. And this is 0.008 meters. And then it goes through the deformation. and we end up with a length in this direction of 0.011 meters. And a length in this direction of 0.007 meters. And we want to do two things. We want to calculate EXX and EYY. And then we want to see if it's a realistic value, if these are realistic values of strains for an engineering material in the operating range. So is this a realistic range of values? Okay, so for EXX, this normal strain is going to be 0.011 minus 0.01 divided by 0.01. And so we get 0.001 over 0.01 or 0.1. And for EYY, we have 0.007 minus 0.008 divided by 0.008. And for that, we get negative 0.125. Okay, so along the x-axis, it's stretched. We see that because we have a positive value. Along the y-axis, it contracted. We can see that because we have a negative value. Are these values in a realistic range? Or are they too big? They're way too big, yeah. So they're way too big to be realistic. That cutoff line, remember, is about 1 times 10 to the minus 4. Okay. Okay, so now let's define the shear strains. And the shear strains deal with angle changes between edges. And I'm going to use a notation where I say, okay, this angle theta AB means the angle in radians between the positive A and positive B faces. And that's going to be important because that's not going to be the same as the angle between, say, the positive A and the negative B face. And this is after the deformation. Okay, so we're going to represent these shear strains this way. We're going to use the Greek letter gamma. And the XY shear strain, so gamma XY, is equal to pi over 2 minus the angle in radians between the positive X and positive Y face, sigma xz, same definition, is going to be pi over 2 minus the angle between the positive X and positive Z faces. And then the last one, gamma yz, is pi over 2 minus the angle between the positive Y and positive Z faces. And again, these are unitless because remember, you can think of radians as just kind of a pure angle. There's no units on radians. So all strains are unitless. And just like we talked about the meaning of the signs of normal strains, you can think of the meanings of the signs of these shear strains. So notice a positive shear strain means the angle gets more acute. And a negative shear strain means the angle gets more obtuse through the deformation. Okay. So let's do an example with these. So let's say we start with this rectangular shape. And I'm going to view this from a funny, from a direction that we're not really used to. I'm going to say that the x-axis, the positive x-axis is up, the y-axis is into the page, and the positive z-axis is over here. Okay. And then the deformation happens, and I'm exaggerating it, but we end up with angles like this. So let's say that we know that this angle is 1.43 radians. Okay. And we want to know what's gamma xz. Okay, well, the first thing we have to do is figure out what the positive faces are. So the positive x face is the face where that x-axis would be pointing, would be like an outward facing normal. So this is the positive x face. The positive z face would be over here. Any questions about that? Same over here after the deformation. So there's our positive x and our positive z. And so the angle that we need in order to calculate this shear strain is this one. Okay. So this is our angle xz that we need. And this is a parallelogram. So this angle, let me write it this way. 1.43 plus this angle xz is equal to pi. And so this angle between the positive x and the positive z face is pi minus 1.43, which is 1.71 radians. Okay. So the shear strain between the x and z faces is pi over 2 minus 1.71, which is negative 0.28. Did that angle get more acute or more obtuse? More obtuse, yep. And you see that because it's a negative sign. What about the magnitude of this value? Is it realistic or too big to be realistic? Yeah, it's too big. And then how do we represent all the values of the strain? You might think that we would have a strain tensor and a Voigt strain because everything looks so similar between the stresses and strains. It turns out that the way we're defining strain, it doesn't meet the mathematical requirements of a tensor. So all we're going to use is the Voigt form. And so the Voigt strain is the way that we're going to represent strains. And we're going to use the same element order as for Voigt stress. And we'll denote it as epsilon sub v, v for Voigt. And the order is going to be the strains in the order, the normal strains in the order you would expect. So EXX, EYY, EZZ. And then the shear strains in the exact opposite order of what you would expect. So gamma YZ, gamma XZ, gamma XY. Okay, any questions about that? Okay, it's early, but I'm going to stop there because I know it's just a ton of talking, writing down stuff. I have some problems I can give you for this. And then we'll go into the constitutive relationship, like the Hooke's law relationship next time. And then we'll be off of all this, just listening and taking notes and stuff. So, okay, go away. So I'll give you a homework assignment that'll be due next Monday.